Okay, welcome back to part 2 of logistic functions, which are going to be a way of explaining growth of populations. So to look at this next example, it says because of limited food and space, a squirrel population cannot exceed 1,600 squirrels. It grows at a rate proportional to both the existing population and to the attainable additional population. And so part A says to write and find the general solution to the differential equation that describes this situation. All right, so recall the general solution is going to be P equals M over 1 plus C e raised to the negative KT. And so we know that M represents your carrying capacity, which in this case is going to be 1,600 squirrels. All right, so we do have these constants in our problem right here and right here that we need to actually find values for. But in order to find those values, we need some additional information. So that's going to take us to part B of this problem. All right, so this says that if there were 100 squirrels 2 years ago and 400 1 year ago, how many squirrels are there now? So that actually gives us two coordinates that we can utilize for this problem. The first one going to be P of 0 is going to be 100 squirrels, and then P of 1 is going to be 400 squirrels. So we're going to let 2 years ago be represented by our initial population. Initial population means that's when time is 0. So then 1 year ago would be P of 1, and then the question asks how many squirrels are there now, which means we want to know what is P of 2 equal to. All right, so once again, we got to find out the values of our two constants, C and K. Now, the importance of having an initial population, or P of 0, is that when we put 0 in for T, that takes this variable, or this constant, it takes both of these things out of our picture so that all we are left with is C, and we can solve for that. All right, so that's going to be our first step, is solving for C. So we're going to start with a population of 100 is equal to 1,600 over 1 plus C, and then once again, e raised to the negative k times 0 is just 1. And so we'll solve like we did in part 1, giving us 1 plus C is equal to 16, and therefore C is equal to 15. All right, so we can substitute that value back into our problem here, giving us P is equal to 1,600 over 1 plus 15 e to the negative kt. Now we use our other coordinate to find the value of k. So that's going to give us 400 is equal to 1,600 over 1 plus 15 e to the negative k times 1, which is negative k. All right, so solving, we're going to get 1 plus 15 e to the negative k equals 1,600 divided by 400, which is 4. Subtract 1 and then divide by 15. It's going to give you 1/5. So the natural log of both sides will yield negative k equals natural log of 1/5. Or in other words, k is equal to negative natural log of 1/5. All right, so we can now substitute this value back into k, and that's going to give us our final equation here of 1,600 divided by 1 plus 15 e raised to the natural log of 1/5 t. And the question was, what's the population now? So that's p of 2, or in other words, we simply put 2 in for t. I'm not going to go through the arithmetic and solving all this, but this ends up being p of 2 is equal to 1,000. So that is the population of the squirrels currently given the information that we have. So now it says, because of limited food and space, a squirrel population cannot exceed 1,600. Same information given. It says determine when the squirrel population is growing the fastest. So when means we need to find that value of t. So let's go back to our equation, which was p is equal to 1,600 over 1 plus 15 e to the natural log of 1/5 t. Growing the fastest. Well, the population grows the fastest when your population is half of the carrying capacity. Half of the carrying capacity would be 800 squirrels. So now we're going to solve this equation for t, giving us 1 plus 15 e to the natural log is equal to 1,600 divided by 800, or 2. So we get e to this power, subtract 1 and divide by 15 is 1 over 15. Take the natural log of both sides, so you get natural log 1/5 t equals natural log of 1/15, or in other words, t is equal to these natural logs divided by each other. Which comes out to 0.317 years ago is when the population was growing the fastest. All right, so next question here says, suppose a flu-like virus is spreading through a population of 50,000 people at a rate proportional to both the number already sick and to the number still unaffected. So we're going to write and find a general solution to the differential equation that describes this situation. Well, the only information we have in this is going to be our carrying capacity of 50,000 people. All right, so that's going to give us dp dt is equal to kp times 1 over p minus 50,000 people. That's the differential equation. The general solution would be equal to your 50,000 carrying capacity over 1 plus c e to the negative kt. All right, so part B is asking if 100 people were sick yesterday and 125 people are sick today, how many will be sick a week from today? All right, so some information that is given, we're going to call yesterday P of 0, our starting population, at 100, which means today is P of 1, and that's 125 people sick. And the question is asking for a week from today. Well, a week from day 1 would be day 8. And so like before, what we're going to do is we're going to use this value to find C, use this value to find K. Once we know those, we can plug this in for T and find our P value. All right, so starting out, we're going to end up with 100 equals 50,000 over 1 plus c. Again, our exponent goes away because it's e to the 0, which is 1. You end up with 1 plus c is equal to 500. Or in other words, c is equal to 499. Substituting back in is going to give us p is equal to 50,000 over 1 plus 499 e to the negative k t. Now we use our other coordinate, and that will give us 125 is equal to 50,000 over 1 plus 499 e to the negative k. All right, so solving, you get 1 plus 499 e to the negative k is equal to 50,000 divided by 125, which is 400. So we got 499 e to the negative k equals 399. E to the negative k is 399 over 499, giving us k is equal to negative natural log 399 over 499. We can substitute that value back into our equation. So we now have an equation that is useful. We have 1 plus 499 e to the natural log 399 divided by 499 t. And we can substitute 8 into t right here, which will yield a final value of 592.534 people are going to be sick a week from today. And then part C says, suppose a flu-like virus is spreading through this population of 50,000. Determine the day when the spread is at a maximum. The spread is going to be at a maximum when the population is at half of the carrying capacity. Half of the carrying capacity is going to be 25,000 people. And so we rebuild our equation with that fact in there. And then we're going to have to solve for t. All right, so solving for t, we're going to end up with 1 plus 499 e to the natural log is equal to 2. And then subtracting 1 and then dividing by 499 gives us 1 over 499. Take the natural log of both sides, and then the dividing, you're going to end up with t is equal to 27.779 days. Okay. All right, so we're going to start the notes here and call this part 2 for the logistic equations. There's going to be one more part to your notes, and so you can look for part 3 at this point in time.